I just did not want to get up in the middle of class and ask people to move around so I can go get a
Fair enough. Alright, you log on your Chromebook? So you can have your handout from yesterday from the lab. All the exit takers just kind of summarize, see where we're at, based on what we learned in the lab yesterday.
one more minute. One more minute. More seconds. 30 more seconds. You finish, close your Chromebook, so I know you're done. More seconds. Close the plug. 3, 2, 1. Alright, solid. Let's talk about why for these questions we did well on. So number 2, which of the following would be considered a covalent compound? C3H8 is the correct answer. Why is the correct answer? Christian, what makes C3H8 covalent? Smell them out. What makes C3H8 covalent? What makes C3H8? Matt?
Two non-metals.
Two nonmetals. Anytime we have two nonmetals, it's a covalent compound. Okay? So, let's look at the next one. Apply it now. Which of the following compounds would have the lowest melting point? CH4 is the correct answer. Why? Santiago. Great, so what type of compound is it? Covalent. So Christian, why is this a covalent compound? Ooh. Two metals would be metallic. Find carbon on the periodic table. Go quick. What side of the staircase is it on?
Non-metals.
Two non-metals, there you go. Okay. So low melting point, non-covalent compound. And the last one, which would conduct electricity, KOH, is the correct answer. Why? Okay, here. What type of compound is KOH? What type of bond? What? Because? Huh? And what else? What about K? Potassium. Okay. So why does this conduct electricity? Cool. Okay. Anytime you have metal, it's going to conduct electricity. Anytime you have metal, it's going to have a high melting. That was the summary from the lab. When is your lab report due? Friday. When is Friday? Friday, yes. The day after tomorrow. Not next Friday, not the Friday after that. Make sure you get your lab report to me on Friday, turn in your notebook. Especially for those of you who I talked to about not having one before, you really need to turn this one in. We also have a quiz on Monday. We'll cover a lot of stuff. We'll cover all your ionic stuff from last week. We'll cover all of our covalent stuff from this week. So it's going to kind of be a big quiz. All right. Photo of the day today. When we did our nuclear energy Socratic seminar, one of the biggest arguments was, oh, living by a nuclear power plant can be very dangerous for our health. And I actually didn't know exactly how dangerous it was. Okay, so I looked it up. And I found this picture that broke it down in a very clear way. We are all exposed to radiation all the time. Okay? So every time you eat food or drink water, you are being exposed to radiation. Okay? In fact, each year, annually, you're exposed to about 30 millirems of radioactivity every year. Millirems are just the unit, there's the units for radioactivity. Okay? Like grams are the units for mass. Okay? If you go and you hurt your arm and you go to the doctor and they're like, oh, let's do an x-ray on you. An x-ray is about 10 millirems of radioactivity. Okay? You get on an airplane and you fly across the country from like San Francisco to New York City, you're exposed to about 5 millirems. So we're exposed to radioactivity all the time. But how much is too much? How much causes health problems? Well, what research has shown, there's no increased risk of getting cancer unless you're exposed to a minimum of 10,000 millirems each year. It's a lot. Okay, 10,000. Under that, there's no increased chance of getting cancer or getting sick or anything like that at all. Okay? Well, let's say you're living next to a nuclear power plant. You're pretty close to radioactive stuff. How much are you getting exposed to? Well, it tells us 0.009. Wow. That's a pretty small number. Okay? Every time you eat a meal, you're being exposed to just as much radioactivity, if not more, than if if the Chevron refinery was a nuclear power plant. Now, if it exploded, different story. But just having it be there, you're not actually being exposed to that much at all. Because I didn't actually know until I looked this up yesterday. Yeah, no. Great question. I don't know. I would assume that it's still way below this 10,000 threshold. If you've ever gotten a CT scan at the hospital, okay, it's kind of imagery that allows doctors to look at, the insides of you in very good detail. That's a lot of radioactivity that is shooting you with. You get 10 CT scans a year. 10 times 1,000 is 10,000. Now you're looking at something that's not good for your health. Okay? So don't go out and break all your arms and legs and have to get CT scans all the time, because then you might have an increased risk of getting cancer. But if there's a nuclear power plant right down the block, we'd be chilling. And now when you're eating lunch today, think to yourself, radioactivity. All right. One objective today. Do you know how to meet our objective?
Students will be able to present covalent compounds using Lewis structure.
Perfect. Okay. So we learned last week, ionic compounds, we said that Na, to satisfy the octet rule, is going to lose an electron to form Na+. Well, Na is a metal, it's going to be an ionic bond. What if you only have nonmetals? What happens then? Okay. So this is a skill that needs to be practiced a bunch, so I'm going to kind of model a few examples up front. And then you guys are going to play around with what's in the plastic bag. You have a bunch of little pieces, kind of puzzle pieces. You're going to build puzzles today. Yay! Yay. Okay? But first, let's jot down a few things about how to draw Lewis structures. Okay? So, first thing, covalent bonds. What are covalent bonds? They are formed between non-metals. So if you have two non-metals, boom, covalent bond. Okay? And the difference in a covalent bond is what's happening to the electrons. Do you guys remember what happened with electrons in an ionic bond? Yeah, it's getting more negative because, think about the bus. What did we do on the bus? Where were we? We were going to Nigel's house? Then we went to Randy's house? Then we went back to Nigel's house? And to do that, we had to transfer buses. Okay, so electrons are transferred in an ionic bond. In a covalent bond, electrons are shared. So non-metals, they went to kindergarten. They learned how to share. Metals, they didn't go to kindergarten. Or if they did, they didn't pay attention. They don't know how to share. They just napped all day. Good life. Okay. Electrons are shared. So how do we draw that? How do we draw that? We represent that with things called Lewis symbols. So I'm going to give you an example of a Lewis symbol and ask you to figure out what it means. So here is the Lewis symbol for carbon. That's an example. That's the Lewis symbol for carbon. Okay. So what I want you to think about is, why is that the Lewis symbol for carbon? Why do you think it's drawn in that way? What do those dots represent? You're going to turn to your neighbor and talk about it for 30 seconds. Go. All right. What do you think those dots represent? Why is this drawn like this? Oh, so. Not sure. Delilah?
Does it give the number of valence electrons?
And how do we get the number of valence electrons?
I will calculate.
Cool, so let's say I'll find carbon on the periodic table. What's the group number with the A above carbon? And that represents what? Boom. 1, 2, 3, 4. Perfect, 11. Awesome. So if I asked you to draw the Lewis symbol for nitrogen, the way we would draw it, figure out the number of valence electrons it has. Say group 5. 5 valence electrons. The way we draw it is not just kind of all surrounding the atom. What happens is we put kind of one on each side and go around. And then once we've gone around once, then they start to double up. And they want to be in pairs. So that would be the Lewis symbol for nitrogen. Okay? Now you guys go ahead and try to draw the Lewis symbol for chlorine, Cl. Give that one a try. How'd you draw the Lewis symbol for chlorine? So, Randy? try just one over here.
Because, I'll look at the numbers up on 7, I'll go to adding 7. The next one?
Exactly.
Okay.
Exactly. Okay. One thing to note, this is the same thing as this. It's the same thing as this. It doesn't matter what side the electrons are on, the pairs or the singles. All that matters is that you have the correct total number. The correct total number. Okay. So, atoms don't exist by themselves. That's boring. They like to get together and react and party. So, let's make a party. We're going to the F2 party. You guys ever been to an F2 party? Oh, if you haven't, welcome. Welcome. Get ready. Prepare yourself. Okay. The way we would draw the molecule of this means we would have to take into account the fact there are 2 fluorines. The way we do this, draw the Lewis symbols for each atom. Okay. So for fluorine, we have 2 fluorines, so we need to draw the Lewis symbols for them first. So there's 1 fluorine in this box. Fluorine's in group 7, so it needs to have 7 electrons around it. 1, 2, 3, 4, 5, 6, 7. I have another fluorine, so I need to draw the same thing. 1, 2, 3, 4, 5, 6, 7. Okay. And once I've drawn the atoms by themselves, I have to combine atoms to make sure they satisfy the octet rule. Okay. Just with the electrons that I've already drawn. So I can't add any more electrons in. I can't just add a dot here and add a dot there. What I can do is I can take these atoms and kind of go and put them together. Because then, if I draw that in the next box, okay, these 2 electrons that are by themselves are now going to be between both of those atoms of fluorine. So when we said above electrons are shared, that's what this means. They're in between both atoms. Shared means they're in between both atoms. And then we still have to draw the other electrons that were around the atoms to start. Okay. Now we got to think, does each atom satisfy the octet rule? Okay. Well, around this fluorine we have 1, 2, 3, 4, 5, 6, 7, 8. Yup. Now let's check this fluorine. Well, you might be thinking, Shar, I already counted those first 2 electrons, so I don't count them again. That's wrong. If the electrons are in between 2 atoms, they count for both of the atoms. Okay? So around this fluorine on the left, there's 1, 2, 3, 4, 5, 6, 7, 8. So both atoms satisfy the octet. Great. Last step. Draw shared electrons as a line. So the electrons that are in between the 2 atoms, we draw those as a line. Boom. And there's our final answer. That would be the Lewis structure for F2. Okay. 2 lines would be wrong, because that would be for, that's what we're doing tomorrow, that would be if there's 4 electrons in between. Since there's only 2 electrons, that's 1 line. Okay. So Johnny brings up a common misconception. 1 bond, 1 line represents 2 electrons. Every bond represents 2 electrons, not 1. The last thing, you will never have to go, yo Shar, yo Shar, yo Shar. Is this right? Is this right? Yo Shar, is this right? Yo Shar, is this right? Because you can always check yourself. You can always check yourself. There are two things you can do to make sure that your Lewis structure is correct. Number one, okay? Check the total number of valence electrons. The total number of valence electrons has to be correct. So what do I mean by that? Let's think about F2. Each atom of fluorine had 7 electrons to start. So if I have 2 atoms of fluorine, 2 times 7 would give me what? 14. 14 electrons. So check, are there 14 electrons in the last thing that we drew? Let's check. 1, 2, 3, 4, 5, 6. Remember the bond counts as 2. 7, 8, 9, 10, 11, 12, 13, 14. Yes! Yes! First thing, check it off. Second thing, we already did. Okay? Check that each atom satisfies octet. And we already did that. So if those two things are true, boom! You're done. It's a wrap. Before I release you to build puzzles, I want to check a few things. How many, well, you guys get those notes down. How many total electrons, okay, so think about this, the total valence electrons. How many total valence electrons would be in each of these compounds? So how many total valence electrons would be in this one? How many total valence electrons would be in that one? You have 1 minute to talk about it with your neighbor or your group. Be ready to shout an answer in 1 minute. Go.